Here's two equations. Those are both fundamental equations for electromagnetics. And yeah, there's a lot of stuff there, but it doesn't really convey anything particularly physically. So what we want to do is to take these equations and make an app, look something like this, that you can ask some questions, you can change variables, and you can get answers. So what this is actually an electric dipole in a hole space, and these are the magnetic field lines. So what we mean by an electric dipole is just a piece of wire with a generator attached to it that is grounded to here. So for anybody here in hydrocarbons, anybody who's been involved with seafloor EM, where you're pulling a grounded source in the ocean and then measuring the fields, that's actually what this, that's kind of what this is in a way. So if you imagine, you've got a source down in the ocean, it's kind of like a whole space, and those are going to be the fields. But by looking at this, by asking questions, you can get more insight than just by looking. So how do we achieve our goal? Well, we're going to, first of all, connect to relevant applications. Select then a type of survey that might be useful. Use the apps to explore and ask questions, and then show success through a case history. So that's going to be the kind of the way in which we're going to proceed throughout the day. The agenda today is pretty ambitious, because what I wanted to do, and this is a bit different than what people have generally done, is I want to take you on a journey that goes through the entire aspect of electromagnetics. And if we can accomplish that, then when you have an electromagnetic problem, you'll actually be able to kind of see where you are in here and like which technique should I use. So how we're going to orchestrate the day? I'm first going to start with DC resistivity. And then we'll look at the fundamentals of EM. So DC resistivity, that's the oldest technique. You just plunk some current into the ground, see what you get out. Fundamentals of electromagnetics. And then we'll look at inductive sources. So this is where you just have a loop of wire that is your source. And then we can look at grounded sources. So I said the marine EM is here. Anybody that's doing airborne EM surveys, sometimes you're actually looking at large-scale structures, so you want to appeal to natural sources. How many people here are familiar with MT or magnetotellurics? You guys are pretty shy, I ask you. And then if you're really interested in high resolution and near surface, you've got ground penetrating radar. Induced polarization. So now the physical property shows the frequency dependence, and then time. So that's a lot of stuff. But if we can sort of go through that and you have a vision of like how everything is working in each of these, you'll come away with a much more comprehensive understanding about electromagnetics and where to use it. As I said, that's an ambitious schedule. Some people would take courses on any one of those little elements and be a month or two at university. There's a lot of material. There's also a wide variety of backgrounds here. So that's going to try to reach everybody. And one of the things that sometimes we have had people who are really pretty expert in electromagnetics. So there's, at some point you think, well, there's nothing much I can tell, but I I go for coffee every Saturday morning with my wife, and we meet up with the same people at a local coffee shop where we've been doing this for many years. Every Saturday morning for 23 years now. And when we go in, there's always this little quote of the day, right? And this one I really like. It's by a gal by Doris Lessing. This is the quote. That is what learning is. You suddenly understand something that you've understood all your life, but in a new way. So even if people are particular expert in something, it actually might be today that I can take the same thing, present it to you in a different way, and then it enriches your understanding about the problem. So that's another goal. The DISC is really a 2-day event. That has caused some confusion because the SEG wants it to be a 1-day event. But the DISC course today is actually sponsored by the SEG. Tomorrow, we call it DISC Lab. It's sponsored by my local facility, the Geophysical Conversion Facility. And our goal there is to capture local applications. But we want to find out what you are doing. So as we travel around the world, we can use part of the second day to have people tell us, here's my problem, this is what I'm working on. And here's where electromagnetics has played a role. Or here's my problem, is there any chance that EM could potentially work? I mean, just kind of casual discussion about the realities of using electromagnetics in a problem that you're interested in. And we also, with your permission, like to capture these and share them on the web. So this has been already blossomed into quite an extensive resource. As we're going to India, for instance, we find out, okay, what kinds of problems they're interested there. Europe is different, and places are different, right? Go to Europe, they're not interested in hydrocarbons. They're not interested in minerals. They're interested in water issues. They're interested in pollution of the environment through waste dumps, in unexploded ordnances from bombs. Right? You come to South Asia, and they're mostly hydrocarbons and minerals. Other places, it's tectonic problems. But the great thing about electromagnetics is that it's scalable. It can work with, so you just take the right fundamentals and then you just apply them. So that's our goal. First of all, how many people will be able to stay for tomorrow? So there's just 2, 3?
Not sure.
Not sure. 4. Okay, so that's not very many. We were hoping that virtually everybody would be able to stay. What I will do, okay, well, I think, so generally there's a bit too much material to really cover all in one day, so we swap some of it over in the second. What I'll do then for today is make sure that we've kind of got from A to Z, right? And you can consider that as being the course. And then for those people who can come tomorrow, we can go back and look in more detail at some things or cover a few things that have been missed, and also talk about both of those. So we'll orchestrate it today so that if you can only stay today, you'll feel like, okay, I've kind of gone through the whole spectrum or most of the spectrum and feel like, okay, take it close.
May I give a suggestion?
Yeah.
Just to make a quick survey on what you did and most interested of the audience. So for instance, I don't know how many people here will work with ground geophysics, for instance. Okay, if most of the audience will be working with marine, interested in marine EM, but what so okay, would be kind of short in that portion that nobody will very few people beat the rest. I don't know if it's easy or not to do this quickly, you know.
Well, we did kind of go around. Yeah, so we've gone around. I found out what everybody's interested in, and yeah. So irrespective of what your application is, all of the fundamentals will be important. So, for instance, if you are interested in marine EM, okay, then there's two parts of that that are really important. One is DC resistivity, okay, and the other is inductive sources. They're both part and parcel. So we're going to parse these things out step by step by step so that you really understand them. Building on something that's more complicated towards something that's more complicated by looking at the pieces is actually a good way to go. So we'll do that, but where the flexibility comes in is in the choice of case histories or how much time you spend on that particular case history. So connecting and contributing, that's another goal for the disk. One of the ways that we've been communicating a lot with people that's worked out very well is something called Slack. Has anybody heard of Slack? So it's just a way of using this as it's a convenient channel to ask questions, make comments, show pictures, and just to communicate. So with most places that we've been, we've established a Slack channel and work. And then contributing, there's EM GeoSci, there's case histories, content, and then there's open source software, which we talk more about, which is Syntax. So this will all be kind of part, especially of day 2. So with that, I'd like to do an introduction to electromagnetics. Just get you online. Can I just get you online? Okay. So there's actually going to be 3 physical properties that are potentially useful for electromagnetics. We're going to concentrate mostly on electrical resistivity. But here's a generic problem. Okay, so for instance, for minerals, how do we locate, characterize them? Maybe you've got unexploded ordnances. Maybe you got water issues. 3 different problems. The thing about those problems are connected with different physical properties. The one that we're of primary concern is electrical resistivity. So this tells you how easily it is to pass a current through a rock material. For instance, so first of all, the units are ohm meters. And here's the scale. It's a logarithmic scale. So that varies by 7 orders of magnitude. Very low resistivities. Quickly. Things like graphites or salt water. High resistivities, rocks, metamorphic rocks, sands, gravels. There's a whole bunch of stuff in between. Much of what we're interested in. Oil, for instance, is 100 ohm meters in here. So hydrocarbons fall into here. They have a lower resistivity. So anyway, that's sort of the kind of summary of the resistivities for various units. Notice if I have a resistivity of 100 ohm meters, that it could be a whole bunch of different things. So you have to bear in mind that there's no unique thing. talking a lot about is conductivity. That's the reciprocal of resistivity. It's per meter or sometimes millisiemens. Rock that has a very low resistivity has a very high conductivity. So electromagnetic people use the terms resistivity and conductivity interchangeably. They're like, oh, one is the reciprocal. Second physical property is the dielectric constant. The dielectric constant of air is 1. 80. Salt water is 80. And other stuff is in between. Quantity becomes very important when we do ground penetrating radar working at higher frequencies.
But the fresh water and still water don't make any difference.
Nope. Yeah, so huge differences in conductivity or resistivity. Dielectric constant. The third problem is magnetic susceptibility. It can vary by many orders of magnitude. And so magnetic susceptibility is the ease with which a rock can acquire a magnetic field. Yeah, so we've got large susceptibilities for things like magnetite. So this is very important for mineral applications. And then can come down to 10 to the minus 5. All the problems that we're going to work with kind of have this scenario. Okay, we've got a source into the ground, and now we've got these physical properties that we're going to interact with, and then that's going to produce some data. That's the general problem. Equations. These are Maxwell's equations. I told you this course is not going to be mathematical, but there is a slide that it will bring up at various times in the day just to kind of tell you what's going on. On the left-hand side here, we've got an equation that relates a time-varying magnetic field to an electric field. So E is electric. That's called Faraday's law. So we're going to use that. That's going to be the basis for EM induction for any kind of loop sort airborne surveys. This is at the heart. Ampere's law. A current is going to generate a magnetic field. These down here, they're called constitutive relationships. These are developed in the laboratory, looking at chunks of rock. It tells you the relationship between conductivity and a current density. These that you measure in the lab. This can be written either in the time domain, like this, with small letters, or in the frequency domain, in which you got count. The thing about those equations that once you supply them with a source, like what the source is, and the boundary conditions, everything electromagnetically. I mean, look around you. You've got your cell phones, you've got the projector, you've got these lights. Everything that exists that's connected with transmission of signals to running power grids or whatever, everything. So let's just try to parse things out a bit. And let's first of all look at the sources. So remember, here was our cartoon. So we need to have an energy source. Well, what do we have? We could take just and put a current. That's going to be called an inductive source, just because it doesn't have any contact with it. The other is that you could have a grounded source. I could take a wire, put a generator up to it, attached to probes in sources. But then now I've got a generator. It's putting in a current waveform. What is it? It could be a harmonic, or it could be something that is transient. It's got maybe an on time. And then finally, for my transmitter, where should it be? Could be in the air, could be on the ground, could be in a borehole. So those are my options. So even for sources, our data. Well, what can we measure? We can measure, so we can take two probes and put a generator or put a voltmeter in there, measure electric fields, or we could measure a magnetic field. Field, we've got E and B, or frequency in the time. And then if you're measuring in frequency, well, which frequency do you want? You know, low frequency or high frequency? In time, you want which times do you want? And then finally, you also, these are fields, so you've got components. I could have an EX component or an EY component, whatever I want. And then, where are these things? Are they on the ground, or are they in the air, or down in the side? So again, a lot of potential. So with those three problems that we had, the interesting thing is electrical conductivity is diagnostic for each of them. Let's now just basically take a look at the electrical conductivity. And the first one we're going to look at is DC resistivity. How many people have been involved in a DC resistivity survey? Never heard of DC resistivity. That means everybody else has not been involved that they've heard of it. Does that work? Okay, so okay, so we're going to do a DC resistivity survey. Again, we're looking for structure inside resistivity, rho. And again, resistivity, conductivity, recipients. So what's our motivation? Well, maybe minerals, issues, oil and gas, groundwater, geotechnical, a whole range. And as I said, DC resistivity is one of the oldest experiments that has been. So let's look at electrical conductivity. I showed you this before. It varies over many orders of magnitude. And the reason for that is electrical conductivity is kind of a complex thing. It's a bunch of different things here. I don't know if you can see this at the back. There's a little chunk of rock, and here is a small coin. If you look at this particular, just 10 centimeters on each side, there's a lot of things going on. So there's a textural difference between what's happening here and here and here. So there's three different types of rocks. Different in each of these guys. In order to conduct electricity, we have fluids. How things go depends upon the pore structure, how they're connected. And then it's inside salty, it's not. And then there's the solid matrix. So that's potentially complicated. So what I want to do is kind of go to outline the basic DC experiment and just talk about some of the things that contractors will mention and to give you some idea about. And then we're actually going to go through a case history for a minerals expert. So here's an example. It's for minerals. It's a target mineralized body underneath here. So the overburden is 12 ohm meters, so low resistivity. The host rock is 200. An ore body in here, low resistivity, that's the mineralized zone. And then there's this blue region on here, which is experiment. I take a transmitter, hook it up to 2 probes. I'm going to put current into the earth. So when I do that, the currents will flow through this positive electrode. Associated. We're going to do this bulk of it. So that was the experiment. How do you obtain resistivity out of that? The full equations were like this. But now the term is DC, which means steady state. That means everything really simplifies. To that, and eventually we can combine things into all the terms. Is probably one of the most important equations in a lot of the sciences. It governs fluid flow in media. Here it works for electric potential. If you're not particularly familiar with upside down triangles, doesn't really matter. If you have a homogeneous medium with some conductivity sigma, then there's an exact solution to this problem that says that the voltage is given by this expression. So we have, for a simple problem, homogeneous medium, we have an exact solution. So let's look what that does. First of all, if I put a current in the ground, then where's the current going to flow? Well, if it's uniform ground, then it's just going to flow out. And the electric potential that I see looks like this. So it's actually infinite right at the current electrode, and falls off as 1 upon r as we go over it. Okay. So suppose that was the case. That was the case that I had. What happened if I measured the electric potential at some particular place? Potential here, and can I do anything with that? Can I get some information? Yeah, because we can take this here that we have modeling potential. Let me just rearrange it, and we can write that rho is equal to this. So that means if I measure the voltage, and I know R, that's the distance here from my current to my location. And if I know the current, then I get the resistivity is equal to, in this case, 500 ohm meters. which was exactly what the resistivity was. So this is actually kind of interesting, right? So I put a current in the ground. I just measure the voltage someplace else, take that voltage, and just convert it back and say, oh, here's the resistivity. So idea. We can't quite do that in practice. The generator, we have to put 2 probes in. And so we're going to do that. We're going to be consistent. So here's the positive end of the generator A and the return B. So A electrodes. Do that here. Now look how the story is. So here's the current A, there's B. So now the currents are flowing like this. So instead of before, they now have this direction. What does that do to the potentials? Well, the potentials now look infinitely positive here, infinitely negative there. Predict potential differences of any 2 points just by using the previous formula and kind of summing everything for these different electrodes, and I ended up with something that looks like this. So potential difference I measure is just rho times I times this factor, which I can rearrange to be like that. Come along and I measure, I take 2 points, and I could take these 2, I could take these 2, I could take one here, doesn't matter. Measure that potential difference, put that into here, and I get the apparent resistivity is 500 ohm meters. Like the true, the true scenario, because we always have to somehow have 4 electrons. Now let's suppose that. So now I'm going to put in a little bit of a conductive layer. Put in a conductive layer. What's going to happen to these currents?
Move in the it looks for go to the easier part.
Yeah, and the easier path in this case is that top.
I mean, right.
AMIN.
And
So it means as the easiest path. And if we looked at here, if we have a low resistivity module, then that's, you can see that most more of the current is coming in there. So what happens with the measured voltage, looks like that, plug it into here, we get a resistivity of 226 ohm meters. This was 100, that was 500. Do all this, get a number up, it's 226. Halfway in between. And that's why we call this number here resistivity. So that's what you'll hear Jip is part of resistivity. There's an interactive app for understanding and visualizing, so you can change all of the parameters, and then you can see where the currents are flowing to see what the current resistivity is, and fields or currents or things like that. Play around with and give you some information. At least, they're often collected with particular types of geometries. So here's a case, it's called a Wenner array. So it's got equi-spaces between the all 4 of the electrodes. Then there's also something called a Schlumberger array, which is kind of the same, except that the 2 potentials in here are I don't know, anybody heard of Schlumberger or Wenner? Yeah. So those are that. And what's here is that scale size here. A, B of 2. We can get a different apparent resistivity data. That's here's the apparent resistivity as a function of the electrode length, and it might look something like this. So we're going to carry through that. So I'll start with two currents that are really kind of close together. So you can add two currents really close together. And then the currents are just kind of going. The currents are primarily in this upper region here. Measure some potentials. We get that the apparent resistivity is 100 ohm. Okay, so that's sort of intuitive, right? So we're just sort of sampling this region. As we make the electrodes farther apart, and now we get more current that's coming in here. Now the apparent resistivity is 135. It's even larger, it is 239. So you can see as the length of the array is increasing, then I'm gradually to the deeper structure. So that's a really important.
How determine the depth of the source with the rate?
Well, you can see here, I've got currents, some are in here, some of them are going all the way down here. There's no particular hard cutoff that all the currents are above here, or all the currents are above below. Up here. So that's the essence of a sounding, right? So I'm going to start small. So I'm assuming your name is Chris. So I'm going to start small, right? And I'm sensitive to Christian, right? Not farther back. And as I go back more and more, I gradually get currents that are going deeper and deeper and deeper. So I'm gradually seeing, and that's what a sounding curve is. And this is would be plotted like, so this is apparent resistivity. So that's just your data, the length of your survey. And you can see what happens. Small values of the back at 100 ohm meters, and in order to get up to that final value of we're just seeing the same, we actually have to have really big arrays. This kind of understanding is actually extremely important. All kinds of techniques. Basically, it says that the length of your array much larger than the depth to the target that you're looking for. Factors of 3 are pretty reasonable estimate. But it also means if you want to translate for those people into marine EM, carbon layer that's depth, length of your survey, that's 3 times that, so that's 6 kilometers. Which is why these boats, cables, that are 6-8 kilometers long, because they need to be that long to see that depth. So that's a sounding. I want to stress this particular curve is just a data curve. That's not true resistivity, and that's not true depth. In order to do that, we actually have to invert the data. Take our measurements. So here's our data. And we're going to invert them something that's got true depth and resistivity. my research life has been involved in a particular problem and applying it to various we're not going to dwell on that because that's a whole week course in itself. The idea is as follows. Our 1D Earth, we're just going to divide the Earth up into a whole bunch of layers. And then we're going to, the inverse problem, is going to adjust the values of those layers, reproduce the data, as trying to come up with something that's geologically reasonable for the distribution of this. Okay? Pretty easy. So that's the general framework. If we're in 2 dimensions, it's still the same thing, except now it has infinite cylinders. So instead of a layer, we're looking at a cylinder. Instead of now looking at a little prism. Take a mathematical Earth model, have a whole, use a program to adjust the parameters of those. Make sure you fit the data and be geologically sensitive. I want to come back to because charges are extremely important in all aspects of electromagnetic. And here's how they come up. Remember, we were talking steady state, current density, and this says in medium 1. And here's the current density in medium 2. So as the current kind of comes through here, it stays the same. So the same current is here, is going through here. So it's a constant current. J, according to Ohm's law, was sigma times E. So that means that J1 is sigma 1 times E1, whatever. And J2 is sigma 2 times E2, whatever the electric field is. But now we're crossing a boundary. This conductivity here is different from that. It's different from sigma 2. Then what does that mean about the electric field?
Change.
The electric field has to change. So the electric field is going to be discontinuous. And again, from first year physics, you know that the only way that can happen is if there's an actual charge that's built up. A little plate of charge this way and this way. So that means the electric field is discontinuous. Basics now of the DC resistivity survey. We put a current. Currents go through. Wherever there's a change in conductivity, there's going to be charges. Charge is going to give rise to, by a Coulomb's law, where Q is the charge and basically. Okay, so that's the essence of the DC resistivity experiment here.
R and R.
Oh, R is where you are. Okay, R prime is the place in the medium. So it's
That's where the electrode is?
yeah. So R right. So R prime is the source here, and R is where. Let's look at this. So here we've got our cross section. Now we're going to put in a conductive. And here's the currents. So you can see they're kind of doing what I expect, like this, and they're kind of getting sucked in here, and then they're going out. So given that, that are built up like this. So in this case here, going from a resistor to a conductor, there's negative charges, there's positive charges. So this is density that's built on that cylinder. And this is the resultant that we see. So that is essentially what we're going to try to measure. If we wanted to look a little bit more at the currents, what's the total currents? We could subtract from that what we call the primary currents when there was no body in here. We subtract that, and then we get the secondary currents that look like this. Now, it kind of look like a little electric dipole. Right? Secondary currents. Here's our charges, and here's the potential, and this is what we're actually going to try to do. So, what about measuring? Well, let's imagine that we've got a fixed A and B here. So we're going to fix our current electrodes and to look at what would happen if we took a potential measurement in various locations. So just to remind you, we've got a conductive cylinder here, 1 ohm meter, and a 500 ohm meter battery. And that's going to set up these charges, electric potential up here, and a apparent resistivity of 430 ohm meters. Good, right? So the background was 500, and we measured, it's got a lower resistivity. So it seems like, okay, we're actually sensitive to it. We measure away from here. If we measure out here, we have something that's larger than 500, which is a bit odd. Not very much other than 2, but we're going to come back to this because it's actually important. So we got apparent resistivity of 502, which is larger. So in the end, as we're kind of doing a profiling experiment here of moving this guy over, we end up with values that are 502, 430, and 500. But you see, if you're doing that, you can still get some indication of, oh, looks like there's a low resistivity in there, so maybe there's. I want to get the concept of profiling. Okay, so with profiling, we're going to stick with a geometry. So in this case, I'm going to stick up with 2 potential electrodes, and we're just going to move across. So suppose everything is pretty close together here. As I'm the only thing I'm going to see a name, Christian, and Daniela, and Lindsay, right? So yeah, that's it. That's as close as I can see. I can't see a lead name. Not probing into the ground.
Wat verder. Of de zwarte ster die jullie meten, even de
the short offset, remember? Currents that are going like this.
the depth. Oh.
No. So imagine that we do this current resistivities. We're coming to see is this stuff right up here. 500 ohm meters.
I don't see any anomaly here.
No. Okay, so with that really close offset, see
Anything.
you don't see anything. However, bigger, right? And now I move over, Now my currents are going farther into the ground. Right? So now looks at the longer offset. That overshoot I talked a bit about before. But clearly, length, now I'm sensitive to right here.
Alex.
Alex? Okay. At this depth, I can see Alex. That's the other. Summarize then, kind of probing into the earth. In which case, point and make things bigger, 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 and I gradually see down in there. Profiling, in which now I'm kind of sampling at a unit at some particular depth, and I see Lini, and then I see Alex. No problem. There's a whole bunch of different people give. There's Wenner, somebody, we talked about those. Gradient, a gradient array, often you just fix the current electrodes, and then you move the potentials, in and out here. Yeah, some sort of lateral variation. The other quantities that come into play, a dipole, where we actually have two potential dipole. If we take one of these electrodes and we just run them way and heck and gone up there, maybe drag cable a couple of kilometers in some cases. Effectively, that electrode doesn't affect anything, and so we kind of have like a pole dipole potential, or we could run the other electrode out and we have a pole. So you hear these words. So you very often end up using like a pole dipole. But fundamentals are all the same. So how do you plot the data? To have some way of plotting. We're going to do, which is generally what's called a pseudo plotting the data. So for instance, if I've got a dipole. So I need to plot it on a piece of paper. I'm going to do it in the following manner. I'm just going to draw a 45-degree line here, and where they intersect to plot the apparent resistivity. So I could measure resistivity. I'm going to plot that value right here. If I move this guy out, here, with that sort of makes sense, right? I'm apart, so somehow I'm looking deeper. So I'm going to plot this point a little deeper. Okay, so that's a way of just sort of plotting those data, and then I can move everything over and do that same thing. So moving. Okay, so kind of got what was happening. I can play it once more, but we gradually are do that. So we move that out. So keep moving over. Just plot these values, and then eventually we got this color blue. That is an image of the data. That is not necessarily geology. And this is where there's always been a lot of confusion, at least used to be. There's perhaps becoming less and less, but still people are really tempted if you want to find a low resistivity zone, you're looking for a conductor, it's tempting to kind of, put a drill hole through here or here, right? But go ahead.
If you want to see a little shallow, what will you do?
If you want to see shallow, then everything has to be small, close to the surface.
This is a problem of this. Very tight. You just see the weather zone, and there's no conductor inside because everything is just weather. It's going already.
Right.
So pipe is going already. So targets are very thin. And you have to see deep. Maybe to 50 meters. It's very difficult to reach because you have to remind the distance of the pole. It's been a challenge for us here because of the weather.
Okay, so that's something that's worthwhile exploring, sort of the details of, sort of what that geology is, like thickness of the weathered zone, what the resistivities are, what you're looking for underneath. And we can do that. So, but certainly and I'll talk about the effects of the background in just a few minutes here too. So what I want to stress here is that buried body, not only do this DC experiment over top of it, I get a pseudo-section that looks like it's really there. Here's our data. And maybe in this case, the geology is simple enough. There's only a block of aspects. That, okay, if I put a drill hole right through here, I'd have been lucky. Okay? But what happens, whoops, what happens in this case? But I'm putting, just a few pieces of, clays or graphite, something that's conducting up here. Same experiment, look at the pseudo section, and I get that. So there's your image of your data, but you cannot convert that to geology. Got a little bit of a valley. There's two conductors that are sitting up here. The apparent pseudo-section looks like that. This is real tempting, right? So you've got this large red spot down here. Just so tempting to spot a drill hole that goes right through there because you're looking for a conductor. Right through there. Okay? That's a picture of data. So in order to kind of get to some information about the model, we need to invert the data. So we're going to do the same thing that we did before. Collect the data, put it through this process. Now, however, the Earth is two-dimensional. Cells are infinite.
Let's say a word about the true value of the pseudo sections. What's the true value of the pseudo sections? People try to follow, and some people think that can be imaging of the most of the cases it's not. So how is it?
Right. So back here.
Full foundation of the data. I mean, if people try to interpret, you're gonna be. But the real value of the pseudo sections, considering that if people try to make it kind of it's a bit dangerous.
Very dangerous. Yes. So that pseudo section is that at least you can see your data. You can see that, okay, in my my background here might be maybe more yellowish, so maybe it's like 500 ohm years, sort of a background. I think it's a quality control is the best thing, right? Because suppose I've got this guy, this particular point here, he's green, or if he's blue, you think like, oh, maybe there's a incorrectness there. Invert these data, and now if I take that, this resistive amount, so remember here was here's my, if I go and invert these data, now here's my recovered resistivity. So that's pretty good, right? So it's at the right location. It's not a fair edges, but the inversion algorithm I've been using is one that kind of smooths off. It's looking for something that's globally smooth. So that's
In the
all.
same method. Always the same method.
Yeah. Well, this is my model. Here's my data. Okay. Now I invert that. I predicted. That's to be compared to that. This has got a lot of noise in it. So look at this one. So here's the one that had all of these clays and stuff on. So here's my pseudo section. If I take that pseudo section and invert, now I end up with this. So this is great, right? So now I recover my block and these things. So I mean, maybe that's just geologic noise, you don't care about it, but yeah, maybe it's something useful. But whatever, I now have an image of, you can see, could not have made that interpretation. This was resistivities. If I invert them, this is what I get. So I now have two targets here. And yeah, I don't see this bottom part, but that's because the resolving power of my experiment is not, I don't have enough, electrodes. So, but basically, I've unraveled the complexities of what the geology is. Okay, so the important points here are just a plot of the data. Everything needs to be inverted, and properly you can get out some reasonable estimates.
What is in that last experiment you have the topography? What is the role of topography to the inversion?
Topography in what is the role of it? It distorts.
Yeah. How it does distort the image if it is not included in the
Oh,
data.
huge.
Yeah.
Huge. Topography is really
like if you use a software where it does not consider.
Yeah, you're going to likely have artifacts.
Mm-hmm.
Actually, going to be causing. I remember I talked about charges.
Mm-hmm.
Okay, so if you've got a mountain or something like that. Okay, then you're going to get charges that are built up there, and it's going to screw up. Okay, so far we've just kind of been taking small steps to understand what's going on, and we're okay for 2D. So now things get more complicated, right? Because what's the size, the shape, background, resistivity. Isn't like, how is it affecting us? And then you have this question like, okay, I'm trying to find maybe an ore body here or something. Okay, where do I put my currents? Yeah, and where should I make my measurements? Should I make an EX, an EY? What are the effects of topography? Here's your survey design questions. And to think about them, we actually need to think about sensitivity. So if I were to ask somebody, okay, what do we mean by sensitivity within the concept? Alex?
How much the data would change your target?
Okay, that's pretty good. It's like this. So we got a target, and we're thinking, well, let's take a data. Put another current and take it up here. Let's measure this. So now we could measure this, let's say, with the target or without, or we could measure it, see if it's the lap change of it, or maybe just the resistivity, any parameter. At how much the data changes when we change that parameter, what you said. So it's the change in the data by the change in the model. Big, then we know, like, okay, good data to take. I'm going to take that data. Usually when people talk about sensitivities, they just kind of go right to the end, say, okay, well, here's the sensitivity. But rather to proceed in two steps, because two parts of sensitivity that you need to excite the target, and then the second is that you need to take a measurement. Helpful to think about these two things being separate. So let's do that. So let's think about exciting the target. Current, as we did before. Here, put the currents in so you can see. Yeah, quite clearly, all these charges that are built up. So source, that's pretty good. Well, the measurement is kind of intuitive, right? Because we've got these charges here to put ends of our potential levels in proximity to that. So we really want to be as close as possible. To the surface of the Earth, then that's fine. We probably move along. What we'd see here is that measurements here are actually going to be pretty sensitive to the existence of this target, and especially this guy that's sitting right here. So, basic elements, we need to excite the target, and we're going to do this doing continually throughout the day. Here I'm plotting charges, but in a lot of cases for this afternoon, we're going to plot currents. So we need to be able to generate currents in an object. Here we need to be able to generate charges. Then now you know that you want to have your measurement somehow as close as possible to this charge. So the one thing we haven't talked about is coupling. We take a thin plate. But here's our A, here's our B. Take a thin plate, and we can move it this way, or we can move it this way, or we can lie it on the side. So there's a lot of different orientations that one could. And then the first thing is like, okay, does that make a difference? A line like this, you can see how the currents are kind of going. And there's sort of. If it's horizontal, it's lying on its side. Now you can see that we've got a major distortion in the currents. So that's going to mean that these things are going to produce different coupling. Going to be an issue. And then the question is, so what do you think about this? So suppose that I had a resistive target and the other had a conductive target. Difference, or should there be a difference, or?
Question?
So the question is, I've got a target that looks like this. Okay, so I'm going to measure something. Now suppose I make it a conductive target, or I make it a resistive target. Is it going to make any difference? So suppose this background is 100 ohm meters, and I made this 1,000 ohm meters, or I made it 10 ohm meters. Would we expect it's pretty much the same, or is it going to make a difference? For me? The reason why, or let's just guess.
I don't know.
Okay, well, let's see. And that's good. So this is the thing about numerical modeling, right? So you've got some intuition. You're going to make a guess. You at least make a prediction, like, okay, they're going to be different. And then you might even force yourself, okay, which is bigger?
But it depends on the orientation as well.
Pardon me?
It depends also.
Yeah. So, right? Okay. So, but now if you just if it's resistor, it's conductor.
But depends on what are you expecting in the model.
I'm just looking at the issue right now. Let's suppose we've got a plate. Okay, in this case, we've got a conductive plate. Okay, so we can see how the currents are being kind of sucked in. And here's my charges. So I get negative charges, positive charges. You know, it's a good excitation. I see something. But look at what happens if I put a resistor in. So this is where, I'm sorry, your name was? So Julius says the resistor is going to be, be more influential. And yeah, you can kind of see from this picture that it probably is that the currents can't go through a resistor now. And ultimately that ends up making even bigger charges here. So now we've got positive charges here, negative charges, but these are much bigger than we can move. Notice also, if you haven't already, that the sign of these charges have changed. So when we go from a conductor, we get these negative charges and then positive charges. We get positive charges and then negative charges. The resistor is going to cause bigger problems. So here's our summary. We first of all excite the target, drive currents into that target, and we need good coupling, so that's where the geometry plays a role. Data, we just want to be in good proximity to the target. And the other thing is that you're measuring a voltage. So that's the voltage you measure is going to depend upon the potential electrodes that you bring. And so that has to be a big enough distance apart so you get a big enough voltage. Otherwise, just random noise is going to change. And then the background is important. Some survey design questions. Okay, so again, always, what's the objective? No problem. Just go ahead and do sound. If it's a target body, it's 2D, then you do this profile sounding that we talked about, but you do it perpendicular to the geology. And if it's a 3D body, then you need 3D geometry. So you just need to have sources, transmitters, receivers everywhere. Need to know the background and need to be concerned about other noise sources. For electromagnetics, noise sources could be a fence, or it could be a pipe, or it could be a power line. So different things that you might have for seismic conducting. Survey design for electromagnetics is, I mean, it's complicated. And it's actually probably not much more different than you do for seismic. So suppose that you've got a volume in here and you've got a target conductor that you're looking at. So the question is, do you see this guy? Well, what do? So you first define your geologic model, like this. Then you assign physical properties to every unit. Then you select a survey. So just hypothesize, okay, I'm going to put a current in here. And I'm going to take some measurements someplace. Simulate the data with the target and without. So without the target, it might look like this. With the target, it looks like that. And now you've got some change here in the data. And then you ask yourself, is that big enough? So is that a significant size? And maybe also is it certain greater than the primary? So you look at the total and the primary, look at the difference, and just see if that is big enough at all. If it is, that's probably a good measurement to take. If it isn't, so I want to do a quick case history. This is area in Australia. It's a mineral deposit. So here's Australia. You can't see it very well on this map, but it's sitting up in the north. We're going to parse it out into these 7 steps. See where we go. So here's the setup. Remember in the setup, we're asking, okay, what's the question that we really want to have answered? The question is, first of all, based upon the geology. So it doesn't matter what all these particular colors different. And then there's siltstones in here, and then there's also the question of concern to the okay, can conductive units, potential targets within the siltstones, can they be identified with DC data? Couple of units of siltstones here, and we've got a conductor that might be mineralized. I'm going to find that guy. Two breakout layers, rock units, and we've got the conductivity. The volcanics, conductivity. Okay, so the thing that we're looking for is something called the Mount Nova horizon. High value of conductivity. Those siltstones were moderate conductivity. The Nova horizon should be distinguishable from these other guys. Unit that's potentially problematic, and that is this breakaway shale, high conductivity. There was pretty minimal, but we took it into account. So how to acquire the data? Well, the the geology was kind of, it was sort of 2D, like it was more or less running north-south. So what was done was to take a 2D acquisition and do 10 lines of data across here. So just to give you a scale, that's about kilometers. And then up here is about 6 kilometers. So there's 10 lines of data, and now how was a pole? Remember we talked about that? So there's a current here, and then you're going to measure the electric potential along here, and you move the current over, measure this, current over, measure that, okay? And you gradually build up this intersection for one line. Okay? And then you've got 10 pseudosections for the 10 different lines. Happening. There's something conductive in here, but you know, that's not an informative picture of geology. The other thing I mentioned is that we need to excite the body, and so at this point we're on this side, so we're exciting one direction. But if we change things around on this side, we excite things different. So let's do that. This is what happens if you put the current on that side. Images. Certainly, it's something more conductive. But you know, what's the geology? Where's our mountain over the horizon? You simply can't do anything with this unless you invert the data. And maybe that's again one of the big things that seismology from electromagnetics. In seismology, you're simply making your interpretations by looking at the data. You go through some processes of migration and stuff like that, which are kind of like single steps of an inversion, but you're not really inverting the data. Here, you can't look at the data. So this is what happened. So now we've taken those data. So now we've got 20 pictures. Convert them into one 3D model. So what you're going to see now is a mathematical cube. You've taken the Earth, divided it into a whole bunch of little prisms, and then each prism is given. Each prism gets a final conductivity, such that all of those previous pseudosections are recovered. And here's the final result. So this is a 3D cube of electrical conductivity. And we're going to look at it a couple of different ways. We're going to slice in and back, slice top to bottom. And then we're going to rotate it around, but successively surface value, so that we only see the largest. You notice this really big conductor red on the right. Okay. Final result. This, I think, shows you the power of inversion. We're able to convert those individual pseudosection images into a single geologic model.
Is that your body of the your body?
Yeah. I'll get to that. So, the geologic feature in here is this guy here. That turns out not to be over the horizon. but it actually is shale. So that's.
Where the ore is?
Pardon me?
Where the ore is in the shale? Oh no.
Well, first of all, it's not oil; it's minerals.
No.
Yeah.
No, ore. Ore.
Oh, the ore.
Ore.
Okay. Yeah. So remember, I said the ore was, but not necessarily the highest. What we see from here is that there is something that's happening here that's highly suggestive. Perhaps on this plot it looks. There's somebody that's coming in here. These are all siltstones in here. Particular interpretation. This is black shale unit. It's geological feature, but not economically interested. This is of interest. Now, the conclusion at this point. Again, as I said, this black shale unit is big geologic feature, but not of interest. The one that is of interest here is the from the electrical conductivity. Electrical conductivity is not the most diagnostic for this, but the mineralized body that we're interested in is actually chargeable. So what we're going to do at the end of the day today is this problem, but also introduce something called induced polarization, or IP effect. And we'll see that the combination of this, of the IP data, this mount will be really nice and successful. We're going to break for coffee here in just a minute. I'm just going to kind of really flip through other. So here's information providing, and it's also on the websites. It's in your slides. Activity problem. Have people potentials? Is that so? Self-potential, you simply you just measure the potential. One of the things that's becoming important worldwide is the integrity of dams. So for mining, it's tailings dams, but for other places, it's just right. And a lot of them are filled with basically earth dams. There's a potential for water to be seeping through the dams, and if they seep through the dams, then they're rise to a self-potential signaler. So you can go out with a DC resistivity array of just measures. And the ultimate goal is to try to find inside the dam that are seeping and measure how much. A case history on that. We won't talk about that today, but it's interesting. What I do want to do here backgrounds. This is going to set us up for the next stage. I did with this situation, right? 500 ohm meter background and a vector. So it was great. What happens if I take in this region and put in a, let's say, a really resistive layer? Pardon me?
You're going to block the cryptocurrency.
Yeah. Okay, Ubu says it's going to block. Anybody else?
have to go around.
Can't go through. That's the basic idea, right? So it can't go, the current can't go through. So if there's just a little layer, it could go around. Layer, it just can't go through. This layer in here, they're confined to the upper region. Resistivity across here, I'd end up with 1600 430, but with the resistive layer. And this number is coming purely from, because if I do the same experiment, if I just model this, so this is important, right? I've got a system that could have been well set up, but somehow, if there was here, where you could imagine even a void, crack of air or something in here. I'm just not going to see through that. I moved. What happens if I have a conductor? Oh. Okay.
Goes through.
Got no idea it goes through, and one goes along the conductor. Put a conductor in. So I put a conductor in, and you're correct, it goes through the conductor. And right down into here. So, yeah, and just so now you get a low apparent resistivity because you just have this conductor here. If you do the modeling without that, then okay, so those are two really important. So we've gone through, we've understood, okay, here's the basics of the DC resistivity experiment. This is kind of, you know, have a background of thin, really high resistivity. If I've got a background that's got really high conductivities in some place, I might be a bit trouble. I'm going to leave it there. And then we're going to come back to that problem with that resistance to be able to with EM induction and elevation on the air. Okay, let's step up.
That and do that. I will do sound profile.
Oh,
the most time I mean you do the profile. But when you do, when have to do a sounding?
Oh no, where was the student section?